Welcome to the exciting world of quantum field theory. Today marks the beginning of our quantum field theory series, where we will dive into the fascinating realm of particles, fields, and the fundamental forces that govern our universe. Imagine a world where the classical laws of physics, which describes the motion of planets, the fall of an apple, and the behavior of billiard balls, simply don't apply. This is the world of incredibly small, the subatomic realm, where things behave in ways that challenge our everyday intuition. Now, I know that the mere mention of mathematics and equations can be intimidating, but don't worry, we are going to take one equation at a time, and I'll break things down in a way that anyone can understand. You really don't need to be a genius to appreciate the beauty of quantum field theory. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the first lesson where we are starting with the mathematics and going deep into demystifying quantum field theory. Well, before I begin, I would like to give you a quick look back, and there is a certain reason on that. Now, previous to this video, I have made a couple of videos on certain other areas. For example, these three videos, quantum field theory, gives you a kind of an introduction of the subject, what it is, its historical development, other areas of quantum field theory like quantum electrodynamics, quantum chromodynamics, Noether's theorem, what is quantization of light. I mean to say an overall idea of how to understand, an overall idea of what this subject is all about, divided into three videos. You can go to my playlist on quantum field theory and you can check. This is just an introduction. It creates a kind of a motivation and gives you an idea before we go into the deep intricate details and the mathematics of quantum field theory. Also, you would see that these are the videos which I have created, 1, 2, 3 and 4. The first one was one of the best book that you would read in quantum field theory, and most importantly, part 1, 2 and 3 deals with how to learn quantum field theory. These videos basically emphasizes on the fact that how to learn the subject, what are the best things and what are the best methods, what are the mathematical prerequisites, what are the physics that you need to know, which is the best book, what is the sequence, what are the areas of quantum mechanics that you need to know more or emphasize more, and what are the areas of classical mechanics that you should know more in order to go for quantum field theory. So these are the four videos which you would give you an idea how to learn, what are the methods and what are the mindset that you should have in order to start with the quantum field theory. And the earlier three videos which I just showed you are basically on the basic idea, historical development and understanding of what is quantum field theory all about. Having laid the foundation, now it is time that we start going into the mathematics and the real part of quantum physics coming in the next part of my video. This is what we will start with: Lagrangian formulation and quantum fields. And you would be surprised that we would start with something which we call the study of optics. Now, in this schematic diagram, you can see that the passage of a light ray through a slab of glass. Right? The bending of the light ray near the air or glass interface can be calculated using the known refractive indices of air and glass, which is calculated by the famous Wilbur Snellius in around 1621, and this is known as the famous Snell's law. Nothing extraordinary, isn't it? But here is a fact that prior to Snell's law, there was an Arab mathematician, Ibn Sal, around 984 AD, who discovered the refractive index, and that credit goes to Ibn Sal. In 1662, the famous French mathematician and physicist Pierre du Fermat produced an ingenious method of deriving Snell's law on the basis of what is called the principle of least time. And this states that the path taken by 2 points A and B in a right lay would be that it is the path that can be traversed by the light in the least time. Now, because light travels more slowly in glass than in air, the ray of light across the glass actually will be at a steeper angle, so it doesn't have so much path length in the glass. If the light ray were to be taken to be straight, the line path from A to B would be longer. This is what it calls the principle of least time. The path taken between A and B by a ray of light can be traversed by the light in least time. So this is actually Pierre du Fermat's deduction of the principle of least time from Ibn Sal. What is more important, interesting is this, that this was very graceful. We know that it did not really explain why light would choose to do this. I mean to say, why should light take the path which take the least time, and why is light in such a hurry? So Fermat's principle of least time, it seems like it is telling something, but it is first sight it looks to be very unhelpful. It attempts to replace a simple formula of Snell's law into which you can plug members and calculate trajectories with this principle characterizing the solution of the problem, but for which you need the whole apparatus of the calculus of variations to solve the problem. Fermat's principle is, however, the key to understanding quantum fields, as we will see in the next part of our video. Now this is something which Fermat paraphrased, or you can say deduced, but it really didn't explain why is light in such a hurry. Now I would like to take from the optics to something which is called in classical mechanics, and here is a space-time diagram. This is a particle going from point A to point B, and consider a particle of mass m, this one, which is subject to a force F, which moves in one spatial dimension, say for example x, from point A to point B. Now as shown in the space-time diagram on the left hand side, now here the time is in the horizontal axis and space, as you see, is in the vertical axis. So the exact path, that is x of t, can be calculated using Newton's law of motion, using time as the second derivative, f equals to m followed by a double dot, which I don't need to explain to you. Now this equation can be integrated, which I am not going into that. However, when you stop thinking about that, now this is actually what is called, it gives a solution to the position of particle at every time starting from tau to t. Now this solution actually is something which is called a quantum unfriendly, or it is not a quantum friendly approach, because it gives the position of the particle at every point. But what does quantum mechanics tells? It tells about this. It tells that quantum mechanics, that the measure of the particle's position at time t equal to 0, you can find it at A, and you might measure it at t equal to tau and you find it at B. That means you won't be able to know precisely what it did in between, isn't it? So having the method in which it lets you calculate x of t from a differential equation is actually not a good point. So what we need to know is that we need to have a scientific theory which generalizes classical mechanics into quantum mechanics. With the Newton's law of motion, we can calculate at every point of time, but quantum mechanics tells that you cannot know precisely what happened in between. Now this thing, I mean to say, development of the scientific theory generalized into quantum mechanics, especially were done by these two mathematicians and physicists from different parts of the world, Joseph Louis Lagrange from French and William Rowan Hamilton from Ireland. Now what exactly Lagrange and William Rowan Hamilton did during that time, they actually had no idea that they were doing that would make the dynamics more quantum friendly. Now here is what it is, how kinetic energy, which is symbolized by T, and potential energy V vary during the trajectory of the particle. Now we know that we can plot the kinetic energy and potential energy in a Newtonian law which gives a nice trajectory, but what if we vary? Now Joseph Louis Lagrange's contribution of the Lagrangian and William Rowan Hamilton's Hamiltonian principleofleastaction unknowingly paved the path of quantum field theory, which gave us an opportunity to generalize Newtonian mechanics into what is called quantum field theory. Now let us see this diagram on the left hand side. You see this is a nice trajectory. starting from 0 to tau and moving up to t, and we know that E equals to t plus v. Nothing great about that. Now what about this kind of a diagram, right hand side, and you can see that trajectory is varied. The trajectory is varied by these blue dotted lines, and what we get is that E should be equals to E bar equals to t bar plus v bar. Here t bar and v bar are, what I am doing is that I am trying to mention the variation, or the variation in terms of the trajectories would be the kinetic energy and potential energy, and I would mention it as t bar and v bar so that I can differentiate between the original and the variation one. Now you see the average kinetic energy during the trajectory can be given by this equation. Simple. So I am taking t bar equals to 1 upon tau, integrating with starting from 0 to t. Simple. And the average potential energy during this time of trajectory would be this one. So it would be this one, right? So what we get is that this t and v I have just mentioned will vary as we alter the trajectory. I think that this is quite okay as far as this part of the video is concerned, but in order to vary the trajectory, that means in order to calculate the average kinetic energy and the average potential energy during the variation, we need one simple mathematical tool. Let us look, and I would like to explain in the next part of the video, which is called the functional and functions. What is the difference between them? So let us imagine that we take a function f of x equals to 3x squared, and I try to put it in the machine. Say for example, if I put the value as 1, it will come up as 3. If I put this value as 3, it will come up to 27. Simple. So this actually states that the function will turn the number 1 into the number 3 and 3 into the number 27. That means a function, given a function, a number, it will return another number. So a function here, the definition is a machine which turns a number into another number. I take another equation, for example, f of x equals to x squared. And if I put this into this same machine, it will again give up a number. So a functional is a machine which turns a function into another number. So it is a very subtle difference. A function is a machine which turns a number into another number, and a functional takes an entire function and turns into another number. Here is on the right hand side, you can see it is quite a comprehensive definition. A function is a machine, mathematical machine obviously, which accepts one or more number as inputs and obviously provides an output. But a functional is that which accepts one or more function as inputs and produces a number which is an output. So we can say obviously a functional is a function of functions. Let me give you some quick examples coming in the next part of this video. If I take f of f operates on the function f as follows, we get this one. We integrate from 0 to 1, and hence the given of the function f of x equal to x squared, the functional returns the number this one. Let me show you another example. The function g of f operates on the function f as follows, and it would give this. So hence the given function f of x equal to x squared, this one will result into this 2a to the power 5. This was important because using these functions and functional, now is the time that we look into where we left earlier. So here it is, how a functional changes as you adjust the function which is fed into. Now here I would like to go back quickly into what is called a functional differentiation. So here you see df by dx equal to limit of epsilon going up to tending up to 0. This is nothing extraordinary. This is just a simple calculus. This actually shows that how the number returned by the function f of x changes as I slightly change the number x which I feed into the machine. That's it. Very simple. The question is this one: can we define a functional derivative of a function? Definitely we can do that, and this equation shows this. So here you see I have underlined in red this one. So the functional derivative tells actually how the number returned by the functional, this one, f within braces f of x, changes as we slightly change the function f of x that we actually fed into the machine. So this actually shows that yes, we can actually define a functional derivative of a function, and this becomes extremely important. Why? Let us look in the next part of the video. And I would like to go before that into a small simple derivation. This is the functional of Newton's law of motion, and now we will be dealing with what is called the Lagrangian and the least action. So this is what we left, right? How kinetic energy T and potential energy V vary during the trajectory of the particle. And this was the question. Now I would like to take a quick look back into Newton's second law of motion, which is F equals to ma. And I can rewrite this as F equals to dp by dt. That means what I am doing is that I'm mentioning F as the force, m as the mass of the object, dp by dt is the rate of change of momentum with respect to time, and dv by dt will be this one. This is the rate of change of momentum with respect to time, and I can write this as the acceleration of the object. Now see, if we express this one dv by dt as the derivative of velocity with respect to time, and I use the simple chain rule, I would say the calculus chain rule, and in terms of position, then what we get is this one. I am expressing dv by dt with respect to time and using the chain rule, and this is what I get. F equals to this, and then further we get v equals to dv by dx. Now if I substitute this expression into the original Newton's second law, so this equation expresses acceleration as the derivative with respect to time, and use the chain rule to express it. So v multiplied by dv by dx. Now what I will do is that I will replace this formula into Newton's second law, which will give us this. So here what happens, mx equals to minus dv by dx is another way of representing Newton's second law, specially showing the relationship between mass m, position x, velocity v, and the acceleration dv by dx in one-dimensional motion. Now what I am going to do is that, taking with this expression, I will define something of a classical trajectory, which is this one, mx double dot. That means I am doing a second order differentiation with respect to time. So here you see that Newton's law tells us the classical trajectory of the particle. That means now if I take this equation and do it for the variation which I showed you earlier in the classical trajectory, this red ones v bar and t bar, it actually shows that if you slightly deviate from the classical trajectory, then both the average kinetic energy and the average potential energy will increase or maybe decrease by the same amount. Now this is very central. You see that what we have done is that we have taken the classical trajectory of the particle, and now we are using the deviation using the v bar and t bar, and what we get is astounding. Both the average kinetic energy and the average potential energy will increase by the same amount. Now I can write this equation, so this one t and v is actually denoting the variations along the path of the trajectory. Now I would like to rewrite this equation in a nice manner, which I have done over here, and I can write it in this way. So what actually it tells, this one, the red line and the 0, this actually tells that the difference between the average kinetic energy and the average potential energy is stationary about the classical trajectory. This is stationary about the classical trajectory. This actually shows that there is something special about the difference between the kinetic energy and the potential energy, and this is what is actually written by the Lagrangian. L equals to t minus v, and the integral of the Lagrangian over time is known as the action, which is given by S. This is the most important part of the video, and you can take a pause and look into it. So you see what I have done. So if from this main equation, I have rewritten this equation, and it tells that the difference between the average kinetic and the average potential is actually stationary when we deal with classical trajectory. And this difference is something very special, and it can be rewritten as in terms of L equals to t minus v, which is actually the Lagrangian. And in due course of time, we will see what this S is all about. But now it is the time to find out one more striking feature. What you see is that the action now has a two dimensions, that is energy multiplied by time, and hence it is measured in joules seconds. So it is the energy multiplied by the time, and we will see in the following part of our future lectures that this S is actually nothing but can be expressed as Planck's constant, which is the h, and we will measure it in terms of Planck's constants. But for the time being, this is all that it is a stationary when we deal with classical trajectory, and this can be represented in terms of Lagrangian. So you see, our variation principle connects variations of average kinetic energy and average potential energy, and this can be rewritten also in this way and this way, and this actually leads to this, which is known as the Hamilton's principle of least action. So what is Hamilton's principle of least action? Now this is very central, very important. We can take another video completely to explain more on Hamilton's principle, but what it tells is this one. It actually tells that the actual trajectory of a physical system is the one that makes the action stationary. This means that if we consider all possible trajectories, everything around it that the system could take, it will be given two configurations. The actual trajectory will be the one that makes the action as small as possible. And here is another definition. It actually states that the classical trajectory is taken by a particle is such that the action is stationary. Small adjustments to the path taken by the particle only increase the action. So you see, now you can find a kind of a similarity between why light was in a hurry and Fermat's principle of least action. Isn't it something which is philosophically and internally similar to Hamilton's principle of least action? Now what we have found is that the Hamilton's principle of least action is this one. So it actually tells that if we consider all possible trajectories that the system could take, the actual trajectory will be the one that makes the action as small as possible. That is why Richard P. Feynman, one of his lectures quoted that nature is very lazy. So it also shows that small adjustments to the path taken by a ray of light, that one we determined right at the beginning, that is the Snell's law, lengthens the time taken by the light ray. Because nature is lazy, because the action taken is as small as possible, so it will become slower and lengthen the time taken by the light ray, and all those incidence, angle, etc. forms because of this. So here is a kind of a example which we have shown earlier, and this is the one, the trajectory. So small adjustment to the path of a particle from its classical trajectory. You can see the fine dotted lines is the variation leads to an increase in the action of S. So the Lagrangian L is related to the Lagrangian density, which is this one, which would lead to this one, and finally it would lead to this one. I think this is all quite clear. I just thought to show you, because Lagrangian density is a very important factor, and this will come repeatedly in various episodes of quantum field theory. So where do we come? Finally, what we can tell, let us look into in the next part of the video. What we find is this one. See, in this video we took about two variation principles. What are those? One was Fermat's principle of least time, and another was Hamilton's principle of least action. Now Fermat's principle of least time actually shows, it describes the path taken by a ray of light, and the Hamilton's principle of least action actually shows that path taken by a classical particle. This is all fine, but the question is that why don't we stick to Snell's law? Why don't we use Newton's laws of motion? What was the problem with that? The answer is this one, that is quantum mechanics. So we will see that later in the part of our video, that if we take these 2 points A and B, for example a particle or a trajectory traveling from A to B, instead of going in this way, this is a straight path, it will take this one, it will take this one, this one, this one, this one, all together. That means from A to B involves all possible paths, the sensible one and the weird one. So we actually have to sum them all up, and they are actually associated, what we call is a phase factor. So we are not using Snell's law, we are not sticking to Newton's law, because the path or the particle which travels is not one but many, and we have to use all these factors together. So here is the final crux, I would say, but we can say it in simple language. Most set of paths with different phases will actually lead to contributions which will cancel out, and when the phase is stationary, it will result into non-cancelling distribution. So Fermat's property tells that about the optical length of the path, that is the difference between phase at the beginning and at end of the ray. So that is what Fermat's law in optics tells. William Rowan Hamilton's principles tells that the least action gives us that the action S is given by the constant multiple by the phase wave of an action. Here is what the wave function of a particle in phase wave looks like, and this action S equals to integral of the Lagrangian followed by dt actually is the action, and we will see in the next part of the video that this action actually leads to what is known as the Feynman's path integral. I just showed you that we cannot calculate one, but we have to take all the factors together, and this was formulated and for which Richard P. Feynman got the Nobel Prize in physics is called the Feynman's path integral. So here it is. If the action is stationary, remember, then the classical path which minimizes the action is the one observed and everything else cancels out. And Snell's law and Newton's law are not good enough. Why? Because they does not allow us to generalize the quantum systems. So that is why we use Lagrangian, we use Hamiltonian, because this gives us a very nice footing, a very nice foundation based on the classical path trajectory, taking the Lagrangian, integrating all and taking all those factors which would be, we can formulate and find out the quantum field theory. So here is a quick summary what we did in today's video. We found out that Fermat's principle of least time states that light takes a path which takes least time. We saw that the Lagrangian of a classical particle is given by this, and classical mechanics can be formulated using Hamiltonian's principle of least action, which is this, and both Fermat's and Hamilton's principles show how classical paths taken by a photon or any kind of a particle are ones in which the phase of the corresponding wave function is stationary. So taken ahead together, the agenda for next video would be that we would like to explore what do we mean by action. What are simple harmonic oscillators, mass on springs, and phonons? So we would carry on with the quantum field theory in the second part of the video, and these are the topics that we are covering, and I'm immensely thankful for those who have watched this video and taken up the time. If you really like the video, hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. You can contact me at this email ID, and this is my other channel where I post videos on general theory of relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. That's all for today's video. This is the first stepping stone in quantum field theory, the real mathematics and the real physics. Watch out more, because Physics for Students will be coming up for the next part of quantum field theory and many more interesting videos. Thank you very much, and may the good Lord be with you.